Right now, something we built is falling away from us. It has been falling for almost 50 years. 24 billion kilometers from where you are lying tonight, a machine the size of a small car is hurtling through a darkness so complete that the sun behind it is just another star. It will never slow down. It will never turn around. Nothing out there will stop it, and nothing back here can reach it. It is the farthest object humanity has ever made, and it is still going. Tonight we follow it. From the summer afternoon when a 26-year-old graduate student noticed something impossible on a sheet of graph paper, through the storms of Jupiter and the rings of Saturn, past the last photograph ever taken of Earth from deep space, across the boundary where the sun's influence finally gives out, and then beyond, into the silence. Into 30,000 years of empty coast, through the coldest, most vacant stretch of space the universe has to offer. We will cover all of it. The launch, the discoveries, the dying signal, the golden record still spinning in the void, and what it means that we sent it at all. If a night like that sounds worth spending together, a like and subscribe means we can keep making them. We begin now.
It started with a pencil and a sheet of graph paper. The year was 1965. A graduate student named Gary Flandreau was spending his summer at the Jet Propulsion Laboratory in Pasadena, California, working on a problem most people would have found tedious. His job was to plot the future positions of the outer planets, Jupiter, Saturn, Uranus, Neptune, year by year, tracing where each one would sit in its orbit across the next 2 decades. He was doing it by hand. No computer simulation, no software, just curves on paper, drawn carefully, one orbit at a time. Flandreau was 26 years old. He had not built anything famous. He had not published anything that made headlines. He was a student with a pencil, and the planets did not care about his career. They just moved where gravity told them to move. But sometime that summer, the lines on his paper did something he had not expected. They converged. All 4 outer planets were drifting slowly into an arrangement on the same side of the sun at roughly the same time. Not in a straight line, that almost never happens, but close enough, curved enough that a spacecraft launched from Earth at the right moment could use Jupiter's gravity to fling itself towards Saturn, Saturn's gravity to reach Uranus, and Uranus to carry it on to Neptune. 1 launch, 4 planets, a single trajectory threading through the outer solar system like a stone skipping across water. He checked the math. He checked it again. The alignment was real, and it was rare. The last time the outer planets had arranged themselves this way, Thomas Jefferson was alive. The next time would be 2153, 176 years between windows. If you missed this one, everyone involved in planning the mission would be dead before the next chance came. Flandreau brought the idea to his supervisors. They listened. The concept was elegant and the physics was sound, but the politics were brutal. NASA was already consumed by Apollo. Landing humans on the moon was eating the budget alive. Proposing a multi-billion-dollar robotic mission to 4 planets no one had ever visited was, by the standards of the time, almost reckless. Congress had no appetite for it. The public did not understand it. The idea that gravity itself could be used as fuel, that a planet's motion could accelerate a spacecraft without burning a single drop of propellant, sounded to most lawmakers like a trick. The original proposal was called the Grand Tour. It called for 4 spacecraft visiting all 4 outer planets in pairs. Congress cut the budget. The mission was downsized, renamed, reduced to 2 spacecraft visiting Jupiter and Saturn only. They called it Mariner Jupiter-Saturn. The name was forgettable on purpose. It sounded modest. Safe. 2 planets, 2 flybys. Done. But the engineers at JPL did something quiet. Something that would not show up in any budget hearing. They designed the second spacecraft, the one that would eventually be called Voyager 2, so that its trajectory could be adjusted after Saturn. If the Jupiter and Saturn flybys went well, if the spacecraft survived, if the funding held, they could redirect it toward Uranus. And if Uranus worked, toward Neptune. They built a 4-planet spacecraft and sold Congress a 2-planet mission. Nobody lied. They just left room for ambition inside a budget built for caution. 12 years later, Voyager 2 reached Neptune. Everything that followed, every discovery, every image that rewrote the textbooks, every data point still trickling back across 24 billion kilometers of void, traces back to that summer. A graduate student, a pencil, a sheet of graph paper, and 4 planets lining up in a pattern that would not repeat until everyone in the room was dust. The part that nobody told the public, the part even the engineers did not fully appreciate, was that this mission was never designed to end. 22 hours. That is how long it takes a signal to travel from Earth to Voyager 1 right now. Not 22 hours to send a message and receive a reply. 22 hours just for the signal to arrive. If Mission Control in Pasadena sends a command tonight, the spacecraft will not receive it until tomorrow night. And if Voyager responds, that confirmation will not reach Earth until the night after that. A single exchange takes nearly 2 full days. A conversation conducted at the speed of light across a silence so vast that light itself gets tired crossing it. The distance involved is not a number the human brain handles well. 24 billion kilometers. You can write it down, you can say it aloud, but it does not land. So here is a way to feel it instead. If you drove a car at highway speed without stopping, no sleep, no fuel, no pause of any kind, it would take you roughly 26 million years to cover that distance. The entire history of the human species, from the first stone tool to the screen you are falling asleep near tonight, fits inside roughly 300,000 years. Voyager is so far away that driving there would take 86 human histories, back to back, without rest. And we are still hearing it. That is the part worth sitting with. Across all of that, across 24 billion kilometers of nothing, through a darkness that has no landmarks and no warmth and no reference point of any kind, a 50-year-old machine built with 1970s technology is still transmitting. The signal arrives carrying roughly 20 watts of power at the source. By the time it reaches Earth, the received energy is 20 billion times weaker than what it takes to run a digital watch. The antennas at the Deep Space Network have to be some of the most sensitive listening instruments ever built just to pull that whisper out of the background noise of the universe. And they do. Every day. Someone is still listening. There is something in that detail that goes beyond engineering. A species on a small, warm planet, pressing its ear to the void, waiting 22 hours for a reply from a machine it launched before most of the people listening were born. The patience required for that is not scientific. It is something older. It is the same instinct that makes you wait by a window when someone you care about is traveling. The knowing that they are out there, moving through something you cannot follow, and the small comfort of hearing from them when the message finally arrives. But that message is getting harder to hear. The signal is weakening. Not because the distance is growing, though it is, but because the spacecraft itself is running out of the one thing it needs to keep transmitting. The power is dying. Slowly, predictably, one instrument at a time. And when it finally drops below the threshold that Earth's antennas can detect, the conversation that has lasted 50 years will end. Not with a dramatic failure,
Not with a collision or an explosion or any event worth noting. Just a signal that was there one day and then was not. The question of what happens after that silence, where the spacecraft goes, what it carries, what it means, is where this night truly begins.
The mission almost did not happen. Twice. The first time was political. The second time was mechanical. And the fact that both crises were survived months apart before the spacecraft ever left the ground says something about what it takes to send something into the permanent dark. By 1976, the mission had already been cut once. The Grand Tour, 4 spacecraft, 4 planets, a decade of planning, had been stripped to 2 spacecraft and 2 planets. The budget was approved. The spacecraft were being built. And then one of the Voyager spacecraft developed a fault in its computer sequencing system during testing. The team traced it, fixed it, and kept moving. Months later, a problem appeared in the propulsion system of Voyager 2. Another round of diagnostics, another fix, another delay absorbed into the schedule without breaking it. The launches held. Voyager 2 left Earth on August 20, 1977. Voyager 1 followed on September 5th, 16 days later. The names suggest an order that the launch sequence contradicts. Voyager 1 was given its designation because it was on the faster trajectory, the one that would reach Jupiter first, regardless of which spacecraft left the ground earlier. Voyager 2 would take the longer road. It had more planets to visit, and it could afford to take its time. What the 2 spacecraft carried was, by the standards of 1977, extraordinary. Cameras capable of resolving detail on planetary surfaces from tens of thousands of kilometers away. Instruments to measure magnetic fields, plasma waves, cosmic rays, ultraviolet light. A photopolarimeter to analyze the structure of Saturn's rings. Infrared detectors. Radio systems. The full scientific payload weighed less than 115 kilograms, but it had been designed by some of the sharpest minds in planetary science, each instrument the product of years of argument about what questions mattered most. There was also, on each spacecraft, a 12-inch gold-plated copper disc in a protective aluminum sleeve. But that comes later. Jupiter arrived first, in the spring of 1979. Voyager 1 made its closest approach on March 5th. The images that came back over the following weeks did not just improve on what was known about Jupiter, they replaced it. The Great Red Spot, the storm system that had been observed through telescopes for 3 centuries, turned out to be a structure of staggering complexity. Nested ovals, turbulent edges, smaller storms caught in its rotation like leaves in a drain. The planet's atmosphere was not a flat canvas of bands. It was a dynamic, 3-dimensional engine, churning with a violence that no photograph from Earth had ever suggested. But it was not Jupiter itself that stopped the scientists cold. It was the moons. Before Voyager, Jupiter's 4 large moons, Io, Europa, Ganymede, Callisto, were points of light in even the best telescopes. They had sizes and orbital periods, and that was roughly all. They were known to exist. They were not known to be anything in particular. Voyager 1 changed that in a matter of weeks. And the engineer who noticed the first and most startling discovery was not even looking for it. Linda Morabito was a navigation engineer at JPL. Her job was to process images used for spacecraft tracking, photographs taken to determine Voyager's position against background stars, not science images, not the ones that would appear in journals. On March 9, 1979, 4 days after closest approach to Jupiter, she was examining a navigation image of Io when something at the edge of the moon caught her attention. A crescent-shaped structure rising off the limb, too large, too defined, too symmetrical to be an artifact or a processing error.
It curved upward from the surface like an umbrella turned inside out, rising roughly 270 kilometers above the Moon's terrain. It was a volcanic plume, an active one. Morabito had just discovered the first active extraterrestrial volcano in the history of human observation. Io turned out to have more than 400 active volcanoes. It is the most volcanically active body in the solar system, more volcanically active in raw output than Earth. The source is gravitational. Io sits inside a gravitational tug-of-war between Jupiter and the other large moons, and the constant flexing of its interior generates so much heat that the surface is essentially molten. Lakes of liquid sulfur. Lava flows hundreds of kilometers long, a landscape that resurfaced itself so constantly that no impact craters survived long enough to be counted.
Europa, the next moon out, showed something different, and in its own way more significant. Its surface was smooth and bright, almost too smooth. Crossed by long linear fractures and ridges, the way ice cracks when something moves beneath it. The Voyager images were not detailed enough to confirm what lay under that ice, but they were detailed enough to suggest it. A subsurface ocean. Liquid water, possibly, insulated beneath a shell of ice by heat generated in the same tidal flexing that melted Io's interior. The implications of that were not lost on anyone in the room. Ganymede turned out to have its own magnetic field, the only moon in the solar system known to generate one. Callisto, battered and ancient, recorded the impact history of the early solar system on its face like a geological diary. In a few weeks of flyby data, 4 points of light had become 4 worlds, each stranger than anything the textbooks had predicted. The Voyager team had planned for planets. They had not planned for moons that rewrote the rules of where life might be possible. Saturn was next. And at Saturn, the mission would face a choice from which there was no return. May 2nd, Claude responded. At Saturn, Voyager 1 had to choose. At Saturn, Voyager 1 had to choose. And the choice, once made, could never be undone. By November of 1980, Voyager 1 had been traveling for 3 years. It had crossed the asteroid belt without incident, threaded past Jupiter, and was now closing on Saturn, the ringed planet, the one that had drawn astronomers to their telescopes for centuries. The rings themselves did not disappoint. The Voyager images revealed a structure of breathtaking intricacy, not the 2 or 3 broad bands visible from Earth, but thousands of individual ringlets, some braided, some with sharp edges maintained by the gravitational influence of small embedded moons, some showing wave patterns radiating outward like ripples in a pond. What had looked from Earth like a simple disk turned out to be a machine, an orbital machine of extraordinary precision, running silently around a gas giant 400 million miles from the Sun. But the rings were not the decision. The decision was Titan. Titan is Saturn's largest moon, and in 1980, it was one of the most tantalizing objects in the solar system. Astronomers had known since the 1940s that Titan possessed a thick atmosphere, the only moon in the solar system confirmed to have one. What they did not know was what that atmosphere was made of, how deep it ran, what the surface beneath it looked like, or whether the conditions there bore any resemblance to the conditions on early Earth. Titan was a mystery wrapped in orange haze, and Voyager 1 was the first spacecraft that could actually answer any of those questions. To do it properly meant flying close, very close. The trajectory required to pass near enough to Titan's atmosphere to take meaningful measurements, within 6,000 kilometers of the cloud tops, would use Saturn's gravity to bend Voyager 1's path sharply upward, out of the plane of the solar system, away from any further planetary encounters, forever. There would be no Uranus, no Neptune, no extended grand tour. From that moment forward, Voyager 1's path would arc upward and outward, carrying it away from everything, toward nothing in particular. The mission beyond Saturn would consist entirely of empty space. Ed Stone, the mission's project scientist, led the team through the discussion. It was not a simple one. On one side, the scientific case for Titan was overwhelming. A thick nitrogen atmosphere, possible organic chemistry, surface pressure 1.5 times that of Earth. Titan was, by almost any measure, the most scientifically compelling target in the outer solar system. On the other side, Voyager 2 was still on its way. If Voyager 1 flew past Titan, Voyager 2 would carry the grand tour alone: Uranus, Neptune, the complete outer solar system survey. Sacrificing Voyager 1's planetary future to Titan was only possible because Voyager 2 existed. They chose Titan. On November 12, 1980, Voyager 1 swept within 6,000 kilometers of Titan's amber cloud tops. The data came back slowly, patiently, across hundreds of millions of kilometers. And what it said was this: the atmosphere was 98% nitrogen, the same dominant gas as Earth's atmosphere. Surface pressure was 1.5 atmospheres. The temperature was 179 degrees below 0 Celsius. Complex organic molecules were present in the upper atmosphere, assembled by sunlight, breaking apart nitrogen and methane and recombining them into chains of carbon. Titan was not alive, but it was, in some chemical sense, practicing.
Then Voyager 1 was flung upward, away from the plane of the solar system, and that was the end of its planetary career. Every kilometer since has been a kilometer deeper into nothing. Not toward anything, just away. Voyager 2 continued alone. It reached Uranus in January of 1986. The planet turned out to be tilted on its side, rotating at an angle of 98 degrees relative to its orbit, so that its poles spend decades pointed directly at the Sun, while its equator sits in permanent twilight. Its magnetic field was tilted and offset in ways that still do not have a clean explanation. 10 new moons were discovered in the flyby data. Miranda, one of Uranus's known moons, showed terrain so chaotic, cliffs 10 times the height of Everest, canyons that plunged 20 kilometers into the crust, that some scientists initially proposed it had been shattered and reassembled by some ancient collision. Neptune followed in August of 1989, 12 years after launch. The planet was bluer than expected, more active than expected, whipped by winds that reached 2,000 kilometers per hour, the fastest in the solar system. A storm system the size of Earth, called the Great Dark Spot, churned in its southern hemisphere. And Triton, Neptune's largest moon, turned out to orbit backward, the only large moon in the solar system with a retrograde orbit, almost certainly a captured Kuiper Belt object dragged into Neptune's gravity long ago. Triton's surface was shot through with geysers of nitrogen ice, erupting from a terrain so cold it made Titan look hospitable. Voyager 2 had done it. All 4 planets. The complete grand tour. 12 years. 48 astronomical units from the Sun. But before either spacecraft left the planets behind entirely, one member of the team wanted to do something no one had done before. Something that had nothing to do with magnetometers or plasma wave instruments or ring dynamics. Something much simpler, and in its way, much harder. He wanted to turn the camera around. And the spacecraft drifted on, patient and silent, into the dark. The asteroid belt between Mars and Jupiter is not what the movies suggest. There is no dense field of tumbling rocks, no obstacle course threading through collisions and near misses. The real belt is mostly empty. The rocks that populate it, billions of them, ranging from dust grains to objects hundreds of kilometers across, are spread across a volume so enormous that if you flew through the middle of it, you would almost certainly see nothing. The average distance between objects large enough to notice is roughly 1,000,000 kilometers. The belt is a place where rock is outnumbered by the space between it. Both Voyager spacecraft passed through it without incident, barely noticing it was there. But there is something about the idea of that belt, ancient, cold, unchanged since the solar system's first few million years, that belongs in a moment like this one. Those rocks have been drifting in the same slow orbits for 4.5 billion years. They predate the oceans. They predate the atmosphere. They predate every living thing that has ever existed on Earth. Each one tumbles quietly, catching the sunlight at whatever angle its particular rotation presents, glinting briefly against the black, then turning away again. No one is watching them. They do not need anyone to. Some of them carry iron at their cores, iron forged in a star that died before our sun was born, scattered into the cloud that eventually became this solar system, gathered into these small, cold bodies by gravity, preserved there ever since. They are fossils of a star we will never see. They are patient in the way that only very old things can be patient, unhurried, untroubled, carrying their ancient metal slowly around a star that will outlast every name ever given to it. The spacecraft passed through and left them behind. The rocks kept drifting, as they always have, as they always will, long after the spacecraft is beyond any star's reach. Carl Sagan wanted them to turn the camera around. The request sounds simple. It was not. By February of 1990, Voyager 1 had been flying for 12 years. Its cameras were still functional, but they had not been used in nearly a decade. The last planetary encounter was Saturn in 1980, and there had been nothing worth photographing since. The imaging team had moved on. The cameras were not officially part of the active mission anymore. Pointing them at anything required pulling resources, writing sequences, and spending time that the operations team felt could be better used on the instruments still collecting real science data. And what Sagan was proposing was, by any practical measure, useless.
Earth from 6 billion kilometers would be less than a single pixel. Not a dramatic image of a blue world with swirling clouds and lit coastlines. Not the kind of photograph that ends up in textbooks. A dot. A pale smear of reflected light caught in the scattering glow of sunlight, diffracting through the camera optics. Smaller than a period at the end of a sentence. The scientific value was essentially zero. The resistance was not unreasonable. There was also a genuine technical concern. Pointing the camera in the direction of the inner solar system meant pointing it relatively close to the sun. Not directly at it, but close enough that some members of the imaging team worried about damage to the camera's sensitive detectors. The risk was small but real, and the reward was, by every scientific metric, negligible. Sagan had been making the case for years. Since at least 1980, he had been arguing that Voyager should take one last look back before the cameras were shut down permanently. Not for science. For something harder to defend in a budget meeting, for perspective, for the record, for the species. He kept asking. The team kept weighing it. And eventually, the answer was yes. On February 14th, 1990, Valentine's Day, though the timing was coincidental, mission controllers uploaded the sequence. Voyager 1, now 6 billion kilometers from Earth, turned its camera toward the inner solar system and took 60 frames across a mosaic covering most of the planets. Most of the images showed nothing but the blackness of space and the scattered light of the sun. But in one frame, in a band of light caused by sunlight diffracting inside the camera, a pale blue point appeared. Earth. 1 pixel. 0.12% of a single frame. Sagan saw the image and wrote the words that have followed it ever since. He described a mote of dust suspended in a sunbeam. He described every person who ever lived, every king and farmer and saint and murderer, every moment of human history, every war and every act of kindness, compressed onto that pale blue point. He noted that the Earth was a very small stage in a vast cosmic arena, and that our imagined self-importance was challenged by that point of pale light. He said the photograph underscored our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we have ever known. Those words were delivered as a lecture in 1994, 4 years after the photograph was taken. They have been read and quoted and reprinted so many times that it is easy to forget what they required. They required a graduate student's pencil, a decade of engineering, a 12-year flight, and one scientist who understood that the most important thing a spacecraft can do is sometimes not collect data. Sometimes the most important thing is to turn around and look at where you came from, before the distance makes it impossible. After the mosaic was complete, the cameras were powered down permanently. Not broken, not failed. Switched off, deliberately, to conserve power for the instruments that still had work to do. Voyager 1 could still measure magnetic fields and plasma waves, and the density of particles streaming past it from the sun. But it could no longer see. The pale blue dot was the last photograph Voyager 1 ever took. In the 35 years since, it has traveled another 18 billion kilometers. Everything it has learned since February of 1990 has arrived as numbers: particle counts, field strengths, plasma densities, wave frequencies. The data is rich and scientifically important, and completely invisible to any human sense. You cannot look at it. You can only read it. The spacecraft is blind now, and measuring, and still moving outward at 17 kilometers per second, and the data it was measuring was about to tell us something nobody had been able to confirm before. Something about where the sun ends, and where everything else begins. Nobody knew what the edge of the solar system would feel like. Nobody had ever been there. The concept of an edge sounds clean. A line, a boundary, a moment of crossing. On one side, our solar system. On the other, interstellar space, the medium between stars, the material that fills the galaxy between one sun and the next. In practice, the boundary is not a wall. It is more like a coastline where the tide goes out very slowly, over millions of kilometers, and the distinction between sea and shore depends on what you are measuring. What defines the boundary is pressure. The sun constantly releases a stream of charged particles, electrons, protons, helium nuclei, moving outward at speeds of 400 to 800 kilometers per second. This stream is called the solar wind, and it fills a vast bubble around the sun called the heliosphere. The heliosphere is not a perfect sphere. It is elongated by the sun's motion through the galaxy, stretched into something closer to a comet shape, with a blunt nose pointing in the direction of travel and a long tail streaming behind. Everything inside this bubble is, in a meaningful sense, under the sun's influence. The solar wind fills it. The sun's magnetic field threads through it. It is our neighborhood, defined not by gravity but by the reach of a continuous breath the sun has been exhaling for 4.5 billion years. At some point outward from the sun, that breath runs out of strength. The pressure of the interstellar medium, the thin gas and dust and magnetic fields drifting between stars, pushes back. Where the two pressures balance, the solar wind slows, piles up, and eventually stops. That boundary is called the heliopause. And for decades, nobody knew exactly where it was, because nobody had ever sent anything through it. Don Gurnett had been waiting for it for a long time. Gurnett was a plasma physicist at the University of Iowa, and he had built the plasma wave instrument aboard both Voyager spacecraft. His instrument measured oscillations in the plasma, the charged particles, that surrounded the spacecraft at any given moment. Inside the heliosphere, the plasma is relatively thin and warm, dominated by the solar wind. In interstellar space, theory predicted, the plasma would be denser and colder, and the frequency at which it naturally oscillated would be measurably higher. If Voyager ever crossed into interstellar space, Gurnett's instrument would hear the difference. The pitch would change. He had been listening for that change since the 1980s. The crossing, when it finally came, was not announced by a single dramatic moment.
The data suggested Voyager 1 had been in a transition zone for years, a region called the heliosheath, where the solar wind had already slowed dramatically but had not yet stopped. Readings became ambiguous. Different instruments disagreed about what region the spacecraft was in. The team argued. Papers were published and contested. The edge of the solar system turned out to be exactly as messy as a real coastline. Not a line, but a gradient, and the gradient was wide. Then, in April of 2013, Gurnet's instrument detected something. A burst of electrons accelerating outward from the Sun, the after effect of a solar eruption that had happened 14 months earlier, hit a region of dense plasma and caused it to oscillate. The frequency of that oscillation was 40 times higher than what the instrument had been recording inside the heliosphere. 40 times. The plasma was not solar wind plasma. It was interstellar plasma. Gurnet worked backward through the data, tracking when the density had shifted, and concluded that Voyager 1 had crossed the heliopause on August 25, 2012. It had been in interstellar space for 8 months before anyone confirmed it. The announcement came in September of 2013. For the first time in history, a human-made object had crossed into the space between stars. Voyager 2 followed on November 5, 2018, on the opposite side of the heliosphere from its twin. Its crossing was detected in real time by all 5 of its still-functioning instruments simultaneously. A cleaner confirmation, a sharper moment, the boundary recorded from 5 different angles at once. What the 2 crossings together revealed was that the heliopause was not uniform. The boundary thickness differed on different sides of the heliosphere. The transition was turbulent and layered, threaded with filaments of solar material leaking outward and interstellar material pressing inward. The Sun does not end. It frays. Both spacecraft are now in interstellar space. Not deep interstellar space. They are still close to the Sun in galactic terms, still within the gravitational reach of the Oort cloud that surrounds it. But the medium they are moving through is no longer solar. The particles streaming past them were not made by our Sun. The magnetic field threading through that region does not originate from our star. Voyager is touching material that has drifted between suns for millions of years, undisturbed, until a small machine from a small planet arrived to measure it.
For the first time, we have instruments in the space between stars. And what those instruments are finding is that the transition from our solar system to the galaxy is not a departure so much as a dissolving. The familiar gives way to the unfamiliar gradually, reluctantly, over millions of kilometers, like a language changing one word at a time until you realize you are no longer able to read the signs. Crossing a boundary, it turns out, does not mean the journey is over. In fact, by one important measure, one that most accounts of the Voyager mission quietly skip past, the spacecraft has barely started. If you have stayed with us this far into the night, you are the kind of listener this channel was made for. A like helps more people find nights like this one, and subscribing means something will be waiting the next time sleep does not come easily. We will be here. May 2nd. Claude responded, "Here is the part most people get wrong about Voyager. Here is the part most people get wrong about Voyager. It has not left the solar system. Not really. Not in the way that matters most. When the headlines announced that Voyager 1 had crossed the heliopause in 2012, they were accurate. The magnetic boundary, the edge of the Sun's outward breath, Voyager had crossed it. That is real. But the solar system is not defined only by the reach of the solar wind. It is defined, at its outermost edge, by the reach of the Sun's gravity. And the Sun's gravity extends much, much farther than its wind. Gravity does not run out at the heliopause. Gravity does not run out for a very long time after that. In 1950, a Dutch astronomer named Jan Oort published a paper that would quietly reshape how scientists thought about the outer solar system. Oort had been studying long-period comets, the ones that arrive in the inner solar system on orbits lasting thousands or tens of thousands of years, coming from directions that bore no relationship to the plane in which the planets orbit. They came from above and below, from all angles, as if falling inward from a vast sphere surrounding the Sun, rather than from any particular direction in the orbital plane. Oort proposed that this was exactly what was happening, that surrounding the Sun at enormous distances was a vast reservoir of icy bodies, trillions of them, left over from the formation of the solar system, scattered outward by the gravitational influence of the giant planets over billions of years. This reservoir, which has carried his name ever since, is called the Oort cloud. The Oort cloud begins at roughly 2,000 astronomical units from the Sun. 1 astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers, 2,000 of those. Then it extends outward, growing sparser as it goes, to somewhere between 50,000 and 100,000 astronomical units from the Sun. At its outer edge, the Oort cloud reaches nearly a quarter of the way to the nearest star. Voyager 1, right now, is approximately 160 astronomical units from the Sun. It has not reached the inner edge of the Oort cloud. At its current speed of roughly 17 kilometers per second, it will take approximately 300 years just to reach that inner boundary. 3 centuries of flight to arrive at the beginning of the cloud. And then it will spend another 25 to 30,000 years passing through it, flying through a vast, dark, nearly empty sphere of ancient ice and rock, bound to the Sun by gravity so weak it is almost imperceptible, but still bound. The solar system, measured by gravitational influence, is 2 light-years across. Voyager, for all its distance, for all its headlines and milestone crossings and record-breaking remoteness, is still inside it. It is on a leash. The leash is made of gravity. It is nearly invisible, and it stretches for 2 light-years in every direction. But it is there. This is not a diminishment of what Voyager has done. It is something stranger. It means the solar system is so large that the farthest object we have ever sent into space has been traveling continuously for almost 50 years and has not yet crossed the halfway point to the nearest thing that could reasonably be called the edge. The Oort cloud itself is almost entirely theoretical, not because there is any serious doubt about its existence. The comets it produces are real, and their orbits are consistent with Oort's model, but because it is so distant and its objects are so small and dark that no telescope has ever directly imaged one sitting out there in its natural orbit. We know it exists the way you know a coastline exists from studying the waves that reach you. The evidence is indirect but overwhelming. Trillions of icy bodies, each one a relic of the solar system's earliest days, drifting in orbits so slow and so wide that a single circuit around the Sun takes millions of years.
Occasionally something disturbs them. The gravitational nudge of a passing star or the tidal influence of the galaxy itself pulling gently on the outer fringes of the cloud can dislodge a body from its ancient orbit and send it falling inward toward the Sun. That fall takes thousands of years. The object that eventually blazes through the inner solar system as a comet, visible to anyone who happens to be looking up at the right moment, has been traveling toward us since before human civilization existed. It left the Oort cloud when the pyramids had not yet been built, and it is arriving now. Voyager will pass through this cloud without seeing any of it. The objects are too sparse, too dark, too widely separated. It will cross the entire structure, a sphere tens of thousands of astronomical units wide, and register almost nothing on any instrument. The Oort cloud is presence without visibility, mass without signature. The solar system's outermost architecture, holding its shape in the dark for 4.5 billion years, utterly indifferent to the small machine passing through. And long before Voyager reaches the far side of that cloud, long before it crosses the true gravitational edge of our solar system, something else will happen. Something quieter, and in its own way more final than any boundary crossing. The spacecraft will run out of the one thing that has kept it talking all these years. Voyager runs on decay, not malfunction, not failure, Deliberate, engineered, predictable decay. The kind you can calculate to within a fraction of a watt, decades in advance. The kind that follows a half-life curve as reliably as a clock, because it is, in a sense, the oldest clock in the universe. The slow unwinding of an unstable atomic nucleus into something more stable, releasing heat as it goes. Each Voyager spacecraft carries 3 radioisotope thermoelectric generators. They are cylindrical, roughly the size of a large kitchen pot, and they contain a core of plutonium-238. Not the weapons-grade plutonium-239 used in nuclear warheads, but a different isotope, chosen specifically because its decay is steady and its half-life is long. Plutonium-238 decays by releasing alpha particles, and alpha decay generates heat. The thermoelectric generators convert that heat directly into electricity through a process involving no moving parts, no chemical reaction, no combustion. Just atoms falling apart, releasing energy, and a set of thermocouples turning the temperature difference between the hot core and the cold of space into a trickle of electrical current. At launch in 1977, each spacecraft's 3 generators together produced roughly 470 watts, less than 5 standard light bulbs. It sounds modest, but in the vacuum of space, with no atmosphere to drain heat away, and with carefully designed low-power electronics, 470 watts was enough to run every instrument, every transmitter, every heater keeping critical components from freezing, with margin to spare. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of the remaining plutonium has decayed, and the power output drops accordingly. The drop is not catastrophic. It is gradual, predictable, roughly 4 watts per year. But 4 watts per year across nearly 50 years is almost 200 watts gone. By 2025, Voyager 1 was operating on somewhere around 220 watts, less than 3 standard incandescent light bulbs. The margin that once felt comfortable had become a constraint that shaped every decision the mission team made. The response to that constraint has been a slow, careful dismantling of the spacecraft's own capabilities. The cameras went first, not because they failed, but because they were deliberately powered down in 1990 after the pale blue dot images. There was nothing left to photograph. Then the ultraviolet spectrometer, then the photopolarimeter. Each instrument switched off, not because it stopped working, but because keeping it running cost watts that other instruments needed more. The heaters that kept certain components within safe operating temperatures were reduced one by one, accepting the risk of cold damage to systems that were no longer critical. By the early 2020s, the team was making decisions that had the quality of a long goodbye. Which instrument goes next? Which measurement is most irreplaceable? Which data, if lost, would leave a gap that no future mission could fill for decades? The plasma wave science instrument, which confirmed the heliopause crossing. The magnetometer, measuring the interstellar magnetic field. The low-energy charged particle instrument, counting the cosmic rays streaming in from the galaxy. Each one consuming a small portion of a budget that shrank by roughly 4 watts every year, without exception, regardless of what the team decided. In 2023, an anomaly in Voyager 1's flight data system produced garbled telemetry. The spacecraft was transmitting, but the data arriving at Earth was unreadable, a stream of meaningless, repeated patterns. For 5 months, the team at JPL worked the problem from 24 billion kilometers away, unable to touch the spacecraft, unable to run a diagnostic in any conventional sense, communicating entirely through commands that took 22 hours to arrive and 22 hours to return. They eventually traced the fault to a single corrupted chip in the flight data system. One chip, out of the many that made up Voyager's aging computer. They found a way to route the affected code around the damaged area, rewriting the software in pieces small enough to fit in the remaining memory, transmitting each piece across the void and waiting nearly 2 days for confirmation
that it had arrived and executed correctly. It worked. The signal cleared. Voyager 1 resumed sending coherent data in April of 2024, 46 years after launch. That repair, conducted across 24 billion kilometers on a 46-year-old spacecraft using a workaround no one had planned for, is one of the most remarkable feats of remote engineering in human history. And it bought time. Not much time in cosmic terms. A few more years of coherent data from a machine that is running out of the atoms it needs to stay warm. The engineers who work on Voyager now were not born when it launched. They inherited the mission the way you inherit a very old house, with deep affection, with the weight of its history, and with the knowledge that some things cannot be fixed, only tended. They tend it carefully. They have thought in detail about which instrument they will turn off next, and the one after that, and what the spacecraft will look like in its final configuration, stripped down to the bare minimum, transmitting on the last watts of a dying power source, sending back whatever it can for as long as it can. Sometime in the early to mid-2030s, the last instrument will go dark. Sometime in the early to mid-2030s, the signal will stop. Not with a burst of static, not with a final transmission announcing the end, just a gradual fading, a signal that was detectable one day, becoming indistinguishable from background noise the next. The way a voice becomes impossible to hear, not because it stops speaking, but because the distance finally wins. The spacecraft will still be transmitting. The 23-watt radio signal will still be leaving the antenna, still traveling outward at the speed of light toward a planet it left more than 50 years earlier. But the received power at Earth's end will have dropped below the threshold that even the most sensitive antennas on the planet can pull from the noise. The conversation will not end. It will simply become inaudible. Suzanne Dodd has thought about this more than almost anyone alive. Dodd is the project manager for the Voyager mission at JPL, and she has spent years preparing for an end that she has described as bittersweet, in a way that resists easy explanation. The mission has outlasted every projection. The original design lifetime was 5 years. Then it was extended to cover the outer planets, then extended again for the heliosphere, then again for the interstellar medium. Voyager has been running for nearly 5 times its original design life, through malfunctions and anomalies and the slow arithmetic of radioactive decay. And the team that tends it has developed the kind of relationship with a machine that most people reserve for living things. Dodd has talked about the end of mission planning in practical terms, which instruments to sacrifice last, which data streams to prioritize in the final years, how to ensure that the most scientifically irreplaceable measurements are taken as close to the end as possible. But underneath the practicality is something harder to quantify. The people who work on Voyager know they are the last ones, the last team to hear it, the last humans who will ever know where it is.
The Deep Space Network, the system of giant radio antennas in California, Spain, and Australia that has been listening to Voyager since launch, will make the final contact. The 70-meter dish at the Canberra complex in Australia handles much of the Voyager communication because from the southern hemisphere the geometry of the sky allows the longest, cleanest signal paths. The engineers there will know in the final months that the margin is nearly gone. They will have optimized every parameter they can optimize. They will have pointed the dish with the greatest possible precision. They will be listening as hard as the laws of physics allow. And then one day the noise floor will win. The last confirmed signal from Voyager 1 will mark the end of the longest conversation in history. Over 50 years, across a distance that will be, by then, somewhere around 30 billion kilometers. A dialogue conducted at the speed of light, in the language of radio waves and binary commands, between a species and a machine it sent into the permanent dark before most of the people involved in ending it were born. After the signal dies, Voyager will still exist. That is the part worth holding on to. The spacecraft will still be there, still moving at 17 kilometers per second, still carrying everything it was built to carry. The golden record will still be sealed in its aluminum sleeve on the spacecraft's side, intact, unplayed. The cameras, long dead, will still be pointing wherever they were pointed when the power ran out. The magnetometer boom will still extend from the spacecraft bus. Every component will remain exactly where it is, because in the vacuum of interstellar space there is nothing to corrode it, nothing to shift it, nothing to disturb it in any way. But for the first time since September of 1977, no one will know where it is. Not precisely. Scientists will be able to calculate its approximate position for centuries using known physics. The trajectory is well understood. The forces acting on it are small and predictable. The math is reliable. But the direct knowledge, the confirmed position that comes from actually receiving a signal and knowing the geometry of the antenna, that will be gone. Voyager will become a calculated position rather than a known one, a prediction rather than a confirmed location. It will exist in the solar system the way a thought exists after you have forgotten it, still real somewhere, but no longer reachable. The silence that follows will be a particular kind of silence, not empty, not the silence of something that was never there. The silence of something that was there for 50 years, that spoke reliably and clearly for longer than most human institutions survive, and that is now simply beyond hearing. The spacecraft will keep moving through that silence, patient and unchanged, carrying its record into a dark it will cross alone. And that is where the second journey begins. The one that makes 50 years feel like a morning. Each Voyager carries a 12-inch disc, gold-plated copper, sealed inside an aluminum sleeve, attached to the side of the spacecraft bus. The sleeve is engraved with instructions for playback, a diagram showing the correct rotation speed, a stylus included alongside the record itself, a pulsar map showing the position of our solar system relative to 14 pulsars distributed across the galaxy, each one identified by its precise emission frequency. The map is a return address. The instructions assume a finder with enough scientific sophistication to recognize a pulsar, calculate its frequency, triangulate a position, and then build a device to play a physical record. It assumes, in other words, that whoever finds it is not so different from us. The record was the idea of Carl Sagan, who chaired the committee responsible for its contents. He assembled a small team in 1976 and gave them an impossible task: choose what to say to the universe on behalf of Earth. The budget was modest, the timeline was tight. The philosophical scope was, by any measure, the largest ever assigned to a group of humans working in a single room. Anne Druyan was the creative director. She selected the music: Bach's Brandenburg Concerto No. 2, Beethoven's Cavatina, a Navajo night chant, Blind Willie Johnson playing Dark Was the Night, Cold Was the Ground, a wordless hymn recorded in 1927 by a man who was blind and homeless and sleeping on a wet pallet on the night of the recording, a man whose music Druyan believed represented something essential about human endurance in the face of suffering. Chuck Berry's Johnny B. Good, Georgian choral music, a Peruvian wedding song, 90 minutes of music from across human civilization, chosen by a small committee making decisions that would outlast everything they knew. Druyan also recorded her own brainwaves and heartbeat. She sat in a studio connected to a device that measured her neural activity and cardiac rhythm, and she thought. She thought about the history of the Earth, about the development of life, about human civilization and its cruelties and its moments of grace. And she thought, she later said, about falling in love with Carl Sagan. The two had just realized they were in love, and she spent an hour with electrodes attached to her skull, thinking about it. Those brain waves, the electrical pattern of a human being in the first hours of recognizing love, were encoded onto the record alongside the music and the greetings and the sounds of Earth. A love letter, encoded in neurons, pressed into gold, sailing between the stars on a spacecraft that will still be moving when our sun begins to expand. The record also contains 115 images, encoded in analog audio signals, retrievable with the right equipment. Photographs of the solar system, of Earth's landscapes, of human anatomy, of food, of architecture, of children, of a supermarket, of traffic. Greetings spoken in 55 languages, from Akkadian to Wu Chinese. Sounds of Earth, wind, rain, surf, a thunderstorm, mudpots, crickets, frogs, a hyena, a chimpanzee, a dog, a tractor, a train, a rocket launch, a mother's first words to a newborn child, a kiss. It is not a comprehensive record. It cannot be. The committee knew they were making choices that would exclude almost everything. Every language not represented, every piece of music not selected, every face not photographed. What they were building was not an encyclopedia. It was something more like a held breath. A moment of the species caught and pressed between two pieces of gold, offered to a universe that may or may not be listening, from a civilization that was not certain it deserved an answer. The gold record will almost certainly outlast every other artifact of human civilization. The pyramids will erode. The digital files will become unreadable. The books will crumble. The buildings will fall. In 10,000 years, in 100,000 years, in 1,000,000, there will be almost nothing left on Earth to indicate that anything capable of making music ever lived here. But in the cold vacuum of interstellar space, with no atmosphere to corrode and no radiation energetic enough to erase the grooves, the record will survive. It will be intact in 1,000,000,000 years. It will still carry the sound of rain on a planet that may, by then, no longer have oceans. It will still carry the brainwaves of a woman thinking about love, encoded in the microscopic geometry of a gold-plated disk, drifting through the dark between stars that do not know it is there. The question of whether anyone will ever find it is one that nobody can answer honestly. The galaxy is almost inconceivably large. The spacecraft is almost inconceivably small. The probability of an intersection, even across billions of years, is genuinely low. Sagan knew this. The committee knew this. They made the record anyway. Because the record was never only for whoever might find it. It was for us. It was the act of making it, the choosing, the encoding, the launching, that mattered. The record is proof that at least one species, on at least one pale blue dot, looked out at the dark and decided the correct response was not silence. The correct response was music. In roughly 40,000 years, Voyager 1 will make its closest approach to another star. The star is called Gliese 445. It sits in the constellation Camelopardalis, currently about 17.5 light-years from Earth. It is a small, dim red dwarf, cooler and fainter than our Sun, unremarkable by most measures. It is not moving toward Voyager. Voyager is not moving toward it exactly. They are simply two objects following their separate paths through the galaxy, and the geometry of those paths means they will pass within about 1.6 light-years of each other in approximately 40,000 years. Voyager will not slow down. There is no engine to fire, no fuel remaining, no mechanism of any kind for altering the trajectory. It will pass through the neighborhood of Gliese 445 the way a stone passes through a shadow. Close enough, in astronomical terms, to notice, but far too fast and far too distant to stop. 1.6 light-years is still an enormous distance. It is roughly 400 times the diameter of the solar system measured to the heliopause. Close in galactic terms, unreachable in any practical sense. Voyager 2 is heading in a different direction entirely. In approximately 40,000 years, it will pass within 1.7 light-years of a star called Ross 248, a red dwarf in the constellation Andromeda. Same story, same outcome. A near miss measured in light-years, undetectable to any inhabitant of either star system, registered by no instrument, witnessed by no one. By the time these approaches happen, the spacecraft will have been silent for roughly 38,000 years. The power died somewhere around 2035. The last signal faded into noise. Everything since has been calculated position, a predicted location derived from known physics,
updated periodically by scientists who may or may not still think of these calculations as meaningful. The spacecraft itself has had no awareness of any of this. It has no awareness. It is metal and circuitry and a gold disk, moving through the dark at a speed that feels fast to us and is essentially motionless by the standards of what it is crossing. 40,000 years is a duration the human mind does not handle with any accuracy. So here is a way to feel its shape. 40,000 years ago, modern humans were living in Europe alongside Neanderthals. They were painting animals on the walls of caves in what is now France and Spain. They had language, fire, and tools, but no writing, no agriculture, no permanent settlements. Every civilization that has ever risen and fallen, Mesopotamia, Egypt, Greece, Rome, every dynasty, every empire, every nation-state, fits inside a fraction of the time Voyager will spend crossing the distance between its current position and its closest stellar neighbor. The sun will still be burning when Voyager makes that approach. Our solar system will still exist, but the continents will have shifted into new configurations. The glaciers will have advanced and retreated multiple times. Species alive today will have evolved into forms their ancestors would not recognize, or gone extinct, or both. The descendants of the civilization that launched Voyager, if any exist, will have as much connection to the engineers at JPL as we have to the people painting aurochs on cave walls in southern France. The continuity, if there is any, will be biological and genetic. The cultural memory will be gone entirely, and the spacecraft will be there, unchanged, moving at 17 kilometers per second through a void so empty that it will not have encountered a single atom dense enough to register on any of its dead instruments. The gold record will be intact in its sleeve. The stylus will still be there. The pulsar map will still be accurate. Pulsars slow down over time, and in 40,000 years the frequencies will have shifted slightly, but the map will still be interpretable by anyone patient enough to account for the drift. The spacecraft will pass Gliese 445 and keep moving. There is nothing to stop it. The star's gravity will bend its path by an amount too small to matter, and Voyager will continue outward, into the deeper dark, past any stellar neighborhood, into the vast, empty lanes between the galaxy's spiral arms. In a few million years, it will be genuinely alone. Not near any star, not within any stellar system's gravitational reach, drifting through the interstellar medium in a region so sparse that even cosmic rays become rare. It will still be carrying the record. The sound of rain on a world 4 billion kilometers behind it. The brainwaves of a woman in love. A blind man's hymn recorded on a wet night in 1927. A child's first cry. A kiss. All of it intact. All of it patient. All of it waiting, in the dark, for someone who may never come. And the spacecraft drifted on, patient and silent, into the dark. Voyager did not fail by going silent. That was always the plan. Not the plan anyone wrote down, not the plan that appeared in any budget document or mission timeline, but the plan the universe writes for anything that tries to cross the distance between stars. You build the best machine you can with the materials you have. You aim it carefully. You listen for as long as listening is possible. And then the signal fades, and the machine belongs to the dark, carrying whatever you pressed into it before the conversation ended. We pressed in music. We pressed in greetings in 55 languages. We pressed in the sound of surf and thunder, and a mother's voice and a kiss. We pressed in the brainwaves of someone falling in love. We pressed in a map home. What Voyager represents, in the end, is not a feat of engineering, though it is that. It is not a scientific achievement, though it is that too, profoundly. What it represents is a decision made by a species at a particular moment in its history. A decision about what to do when you look out at the dark and realize it is very large and you are very small, and the distance between you and everything else is almost too large to hold in your mind. You could respond to that with silence.
Many species might. The silence requires nothing. It costs nothing. It risks nothing. We responded with a gold disc and a stylus and 90 minutes of music and the electrical pattern of a human heartbeat, launched on a spacecraft aimed at no particular destination, carrying a message for no confirmed recipient across a distance that makes the word vast feel inadequate. That choice tells you something. Not about the universe, about us. Voyager is the longest-lasting artifact of human civilization. Everything we have built on Earth, every monument, every library, every hard drive, every stone, exists in an atmosphere, under gravity, subject to weather and decay and the slow erasure of time. Voyager exists in vacuum, beyond gravity's practical reach, beyond weather, beyond erosion. In the cold of interstellar space, the gold record could survive for 1 billion years. 1 billion. The Earth is 4.5 billion years old. The record could survive for 1/5 of that, intact, playable, carrying its cargo of sound and image and love from a planet that may, by then, have changed beyond recognition. We are the only species we know of that has done this. We are the only intelligence we have confirmed that looked at the gap between the stars and said, not with certainty, not with proof that anyone would ever answer, but with the particular human combination of hope and stubbornness, that the correct response to the dark was to send something into it that could outlast us. The Voyagers will still be moving when our sun begins to swell. They will still be moving when the inner planets are consumed. They will be moving, in some form, for longer than human imagination can honestly reach. And they will carry, across all of that time and all of that distance, the most human thing we know how to make. Not a weapon, not a claim of territory, not a warning, a record of rain, of music, of the sound a child makes when it first breathes. That is what we sent into the permanent dark. That is what will outlast us. And if it is ever found, by something patient enough and curious enough and capable enough to read it, the first thing they will hear is us. Not at our most powerful, not at our most certain, just here, saying hello, hoping someone is listening. If this night spent with Voyager brought you a quiet moment, we are glad you were here. There are more like this waiting, long nights with deep space, with old light, with the questions that only come when everything else goes still. Until next time, rest well. The Voyagers will still be out there in the morning. The spacecraft moves through a darkness that has no bottom and no edge. Around it, nothing. The nearest star is 4 light-years away, a distance so large it swallows every human reference point, every comparison, every attempt to hold it in the mind. Between here and there, almost nothing drifts. A hydrogen atom, alone, in a volume of space the size of a house. Then another, much farther on. The interstellar medium is not empty in the technical sense. Matter is present, thinly, patiently, but it is as close to nothing as the universe allows. Cold beyond the reach of ordinary cold. Still beyond the reach of ordinary still. The spacecraft does not know any of this. It moves at 17 kilometers per second, which is very fast by the standards of anything that has ever lived on Earth, and very slow by the standards of what it is crossing. At this speed, crossing a single light-year takes roughly 18,000 years. The nearest star is 4 light-years away. The math is patient in a way that human minds are not built to be. The gold disk on its side catches no light out here. There is no nearby star to illuminate it, no reflected glow from any planet, nothing to make it visible against the black. It exists in a darkness so complete that the concept of visibility loses meaning. The disk is there. The grooves are intact. The stylus rests beside it in its sleeve. All of it is exactly as it was when it left the ground in 1977, preserved by the same void that makes the crossing so long. Somewhere far behind, a yellow star burns. Around it, a small blue planet turns. On that planet, things are happening. Things that matter enormously to the things that are doing them, things that would fill books and rooms and lifetimes. None of it reaches here. The light from that star, if you could see it from here, would be just another point in a field of points, indistinguishable from the rest, unremarkable, one among hundreds of billions. The spacecraft does not look back. It has no eyes to look with. It simply moves, as it has always moved, following the path that gravity and momentum laid out for it half a century ago on a warm afternoon in California, when two engineers checked the trajectory one last time and said, "Yes, that is right. That is where it goes."
Outward. Always outward. The stars ahead are not getting closer in any way the spacecraft can register. They are simply there, as they have always been, burning their slow fires in the dark, indifferent to the small metal thing drifting through the space between them. They have been burning since before the solar system existed. They will burn long after it is gone. The spacecraft will pass through their neighborhood and continue, and they will not notice, and it will not notice, and the universe will hold all of it. The stars, the silence, the drifting machine, the grooves in the gold. With the same patient indifference, it holds everything. It is not lonely out here. Loneliness requires a self to feel it. It is simply quiet. The oldest quiet there is. The quiet that was here before the sun ignited, before the planets formed, before anything on any world learned to wonder where it was or what the dark beyond it held. The quiet that will remain when all of that is done. The spacecraft moves through it, small and intact and carrying its cargo of sound, drifting toward a future so distant that the word future no longer quite applies. Somewhere in those grooves, rain is falling on a world 4 billion kilometers behind it. Somewhere in those grooves, a woman is thinking about love. Somewhere in those grooves, a child is crying for the first time, new to the air, new to the light, not yet knowing how large the dark is or how long the silence runs. The spacecraft carries all of it forward, into the cold, into the deep, into the patient, endless dark. And the cosmos held it gently, as it always has, as it always will.